What if I told you that just months ago, humanity faced its first real test of planetary defense? Not in a movie, not in a simulation, but in reality. An object hurtling through space. A 3% chance of impact. Global emergency protocols activated for the first time in history, and the world held its breath. Today, we're diving deep into the story of asteroid 2024 YR4, a 60-meter space rock that became the first asteroid ever to reach level 3 on the Torino scale. We'll explore how it was discovered on a cold December night, how scientists watched in disbelief as impact probabilities climbed instead of falling, how the world's most powerful telescopes were redirected in a coordinated effort unlike anything we'd seen before, and how this event revealed both the strengths and weaknesses of our planetary defense systems. This is the story of when Hollywood scenarios became real, when astronauts and engineers who grew up watching Deep Impact and Armageddon suddenly found themselves living through it, when the question wasn't if we could detect a threat, but whether we could respond fast enough to stop it. Before we begin, make sure to hit that subscribe button and smash the like. You won't want to miss what happened next, because what we learned from 2024 YR4 could determine humanity's survival when the next threat appears. And scientists now say it's not a question of if, but when. December 27th, 2024. While most of the world celebrated the holidays, an automated telescope system called ATLAS scanned the night sky over Hawaii. ATLAS, which stands for Asteroid Terrestrial Impact Last Alert System, had been doing this same routine for years. Searching, cataloging, monitoring thousands of objects that drift through Earth's cosmic neighborhood. But on this night, something new appeared in the data. A faint point of light moving against the background stars. The algorithms flagged it immediately. Unknown object. Trajectory uncertain. Potential near-Earth asteroid. The discovery was logged as 2024 YR4. Just another designation in a database of thousands. At first, nobody was particularly concerned. Every year, astronomers discover hundreds of new asteroids that pass near Earth. 99.9% of them are quickly determined to be harmless. Their orbits calculated. Their threat eliminated. Usually within days, sometimes within hours. But 2024 YR4 was different. As more observations came in during late December and early January, something unusual began to happen. Something that made veteran astronomers stop and take notice. The impact probability wasn't decreasing. It was increasing. This almost never happens. When a new asteroid is discovered, initial observations are limited. The uncertainty is high. As more telescopes track the object and gather more data, the orbital calculations become more precise. And in almost every case, that precision reveals the asteroid will safely miss Earth by millions of kilometers. Not this time. With each new observation of 2024 YR4, the possible impact window narrowed, but it didn't eliminate the threat. By early January 2025, the astronomy community was paying very close attention. Whispers began spreading through professional networks. Conference calls were held. Emergency meetings convened. The target date was December 22nd, 2032, just over 7 years away. Now, let's talk about the Torino scale, because understanding this scale is crucial to understanding what happened next. Imagine a color-coded system designed to communicate asteroid threat levels to both scientists and the public. Created in 1995 by Dr. Richard Binzel at MIT and refined in 1999, the Torino scale ranks asteroid threats from 0 to 10. 0 means no hazard. The object will miss us or burn up harmlessly in the atmosphere. 1 means normal. Impact is extremely unlikely, and the asteroid usually gets downgraded to 0 within days. 2 is where things get interesting. Yellow zone, meriting attention. A close pass that deserves monitoring, though impact remains very unlikely. This level is relatively rare. Then we reach 3. Orange zone. Concerning. This means greater than 1% chance of impact with potential for localized destruction. Think of the Tunguska event in 1908 when an asteroid exploded over Siberia, flattening 2,000 square kilometers of forest. No asteroid in recorded history had ever reached level 3. Until 2024 YR4. On January 27, 2025, it happened. The International Asteroid Warning Network made its first ever official notification. 2024 YR4 had been classified as Torino Scale Level 3. The impact probability had climbed to over 3%. 3% might not sound like much, but consider this. Would you board an airplane if there was a 3% chance it would crash? Would you cross a bridge with a 3% chance of collapse? For an asteroid impact, 3% is absolutely terrifying. The news began to spread beyond the scientific community. Media outlets picked up the story. Social media exploded with speculation. Some people panicked. Others dismissed it as hype. Conspiracy theories emerged almost immediately. Was this real? Were governments hiding something? Why hadn't we heard about this sooner? Behind the scenes, the machinery of planetary defense was grinding into motion. The International Asteroid Warning Network had been established in 2014 following the Chelyabinsk meteor explosion in Russia that injured over 1,500 people. That event had been a wake-up call. A relatively small object, only about 20 meters across, had caught everyone by surprise. It exploded over a populated area with the force of 30 Hiroshima bombs. 2024 YR4 was 3 times larger, 60 meters in diameter. The potential for destruction was significantly higher. As February arrived, the impact probability continued to climb. February 18, 2025, marked the peak, 3.1%, the highest it would ever reach. Observatories around the world were now dedicating significant resources to tracking this object. But they needed more. They needed the big guns, the world's most advanced telescopes, instruments so powerful and in such high demand that every second of their observing time is precious and carefully allocated months in advance. This is where directors' discretionary time came into play. The directors of major observatories have the authority to interrupt scheduled observations for emergency situations, and this qualified. The Catalina Sky Survey in Arizona, the Gran Telescopio Canarias in Spain, the Very Large Telescope in Chile. One by one, these giants of modern astronomy turned their gaze toward 2024 YR4. Scientists needed answers. How big was it exactly? What was it made of? How fast was it spinning? Was it a solid rock or a loose rubble pile? These details weren't just academic curiosity. They were critical information for understanding the threat and, if necessary, planning a response. Because here's what most people don't realize. Not all asteroids are created equal. A solid metallic asteroid is incredibly dense and difficult to deflect. A rubble pile, basically a collection of rocks held together by weak gravity, might break apart under stress, but is also harder to push effectively. The composition determines everything. How much energy would be needed to deflect it? Whether a kinetic impactor would work? Whether nuclear options would need to be considered? By early March 2025, data was flooding in from observatories across the globe, and the picture was becoming clearer. The rotation rate was the first major clue. 2024 YR4 was spinning fast. Really fast. Its rotational period was just 19.5 minutes. This was significant because rubble pile asteroids typically can't spin that quickly without flying apart. The centrifugal force would overcome the weak gravity holding them together. This suggested 2024 YR4 might be a more coherent object, possibly a solid or partially solid body. Then came the spectroscopic analysis. By studying the light reflected from the asteroid's surface, scientists could determine its composition. The data suggested it was either an SQ type or K-type asteroid. SQ types are silicate-rich, composed of stony materials and some metals. K-types are relatively rare, also stony but with different mineral compositions. But here's where things got strange. Different observational platforms were reporting different albedo values. Albedo is the measure of how reflective a surface is. A high albedo means the surface is bright and reflective, like ice or light-colored rock. Low albedo means it's dark, like charcoal. Why would different telescopes see different reflectivity? There were several possibilities. Perhaps the asteroid had an irregular surface with patches of different materials. Maybe one side was darker than the other. Or perhaps there was something about the observation conditions that was affecting the measurements. Some researchers began to wonder, could there be something unusual about this object? Something we weren't quite understanding? Then came March 26, 2025, the day the James Webb Space Telescope entered the story. JWST, the most powerful space telescope ever built, had revolutionized astronomy since its launch. Operating in infrared wavelengths, it could see things invisible to optical telescopes. And when it turned its golden mirrors toward 2024 YR4, it captured images that would prove crucial. The infrared observations allowed scientists to estimate the asteroid's size with unprecedented accuracy, 60 meters in diameter, plus or minus 7 meters, about the size of a 15-story building. Not large enough to cause global devastation, but more than sufficient to create catastrophic damage on a regional scale. To put this in perspective, the Tunguska event in 1908 was likely caused by an asteroid between 40 and 60 meters across. It flattened 80 million trees over an area of 2,000 square kilometers. If 2024 YR4 were to impact a populated area, millions of people could be at risk. But as March progressed and more data accumulated, something remarkable happened. The impact probability for Earth began to decrease. This is what's supposed to happen. This is the normal progression. As observations become more precise, uncertainties narrow, and in almost all cases, the threat evaporates. By late February, the probability had dropped below 3%. By early March, below 2%. By the end of March, below 1%. And finally, on April 23, 2025, NASA made an official announcement. Based on refined orbital calculations, 2024 YR4 posed no significant impact risk to Earth in 2032 or beyond. The threat was over. Earth was safe. People celebrated. The news cycle moved on. But wait. Because in those same orbital calculations, buried in the data that cleared Earth, scientists found something else. Something that made them go pale. The Moon. While Earth's impact probability was dropping to zero, the Moon's probability was climbing. Fast. By May 2025, when optimal viewing conditions ended, the numbers had settled at 4%. 4% chance of lunar impact in December 2032. Higher than Earth's threat had ever been. Now here's where most people make a fatal mistake. They think, okay, so it hits the Moon instead of Earth. Problem solved, right? The Moon's already covered in craters. What's one more? Wrong. Dead wrong. Because when a 60-meter asteroid slams into the Moon at over 50,000 kilometers per hour, it doesn't just make a crater. It creates a massive explosion. Several megatons. Rock, dust, and debris get blasted into space at velocities high enough to escape the Moon's weak gravity. And where does all that material go? Straight into Earth orbit. Think about the movie Gravity. Remember that scene where debris from a destroyed satellite creates a chain reaction, shredding everything in its path? The space station, other satellites, everything. That's not science fiction anymore. That's the threat we're facing. Scientists ran the numbers. A lunar impact from 2024 YR4 would increase the debris density in low Earth orbit by 1,000 times. Not over years, over 48 hours. Let that sink in. Within 2 days of impact, Earth orbit becomes a shooting gallery. Your GPS stops working. No navigation for planes, ships, or your phone. Starlink satellites, the ones providing internet to millions, shredded. Communication satellites broadcasting your favorite shows, gone. Weather satellites that warn us about hurricanes, destroyed. The International Space Station, with astronauts on board, would have to be evacuated immediately, if there's even time. And it gets worse. This isn't just about losing services for a few weeks. The debris cloud would make low Earth orbit unusable for decades, maybe longer. Every satellite we launch would run a gauntlet of high-velocity shrapnel. Every crewed mission would be a death trap. We wouldn't just lose our current space infrastructure. We'd lose access to space itself. This wasn't about the moon getting another crater. This was about humanity's entire orbital ecosystem being obliterated in less than a week. This raised an entirely new question. If we can't rule out lunar impact, what do we do about it? Do we need to send a mission to 2024 YR4? Not to save Earth, but to protect our orbital infrastructure and future space operations? The discussion shifted from planetary defense to what some were calling orbital defense, a new category of threat that hadn't been seriously considered before. Behind closed doors, space agencies began studying mission options. Could we send a reconnaissance spacecraft to get a closer look at 20L24 YR4? Could we deflect it away from both Earth and the Moon? If deflection wasn't possible, could we disrupt it, break it into smaller pieces that would pose less threat? A research paper published in September 2025 examined these questions in detail. The findings were both encouraging and sobering. For reconnaissance missions, the options looked promising. A flyby or rendezvous mission could be launched as late as 2028 and still reach the asteroid with enough time to gather critical data. These missions would use either chemical propulsion or solar electric propulsion, depending on the available launch vehicle and desired mission profile. The best-case scenarios involved launches in late 2028, which would leave approximately 3 years for spacecraft development, testing, and preparation. In the space industry, 3 years is incredibly tight. Most planetary missions take 5 to 10 years from concept to launch. But it was theoretically possible. There was even discussion of repurposing existing spacecraft or using already built vehicles that hadn't been launched yet. NASA's OSIRIS-APEX spacecraft, which had successfully visited asteroid Bennu, was mentioned as one possibility. Though it was already committed to studying asteroid Apophis, some wondered if mission priorities could be adjusted. A reconnaissance mission would answer critical questions. Is 2024 YR4 truly a solid object or a rubble pile? What is its exact composition? Are there any surprises? Any unusual features that ground-based observations might have missed? Does it have a strange shape, like the cigar-shaped interstellar visitor Oumuamua? Could there be volatiles, ices, or other materials that make it more complex than expected? But reconnaissance alone wouldn't eliminate the threat. For that, you'd need deflection, or disruption. The deflection analysis was less encouraging. To deflect an asteroid, you need to change its velocity by a specific amount at a specific time. The earlier you intervene, the smaller the push you need. But with 2024 YR4, the geometry of the situation was problematic. The researchers found that deflection missions were essentially impractical given the orbital mechanics involved. The delta-v requirements, the change in velocity needed, were simply too high for realistic mission profiles. You'd need either impossibly large spacecraft or propulsion technologies that don't currently exist. This left disruption as the primary option, and disruption came in two flavors: kinetic and nuclear. Kinetic disruption means hitting the asteroid with one or more high-speed impactors, not to deflect it, but to break it apart. The goal is to fragment the asteroid into pieces small enough that they either miss the moon entirely or create less dangerous debris if they do impact. The analysis showed that kinetic disruption missions would be viable with launches between April 2030 and April 2032. These would be similar in concept to NASA's DART mission, which successfully impacted asteroid Dimorphos in 2022, changing its orbit and proving that kinetic impact could work as a planetary defense technique. But there's a critical difference between deflecting a small asteroid and disrupting a larger one. Deflection requires precision, but relatively modest energy. Disruption requires tremendous kinetic energy delivered to the target. You need to hit it hard enough to overcome the gravitational binding energy holding it together. For a 60-meter asteroid, that's a lot of energy. The mission would likely require multiple impactors, launched on separate vehicles, all timed to strike within seconds or minutes of each other. The complexity would be immense. The cost would be astronomical, potentially billions of dollars. Then there's the nuclear option. Nuclear disruption missions were assessed to be available with launches between late 2029 and late 2031. These would involve sending a nuclear device, not to explode on the surface, but to detonate near the asteroid, or potentially inside it if a penetrator could be deployed. The energy released by a nuclear explosion, even a relatively small one, dwarfs anything achievable with kinetic impactors. A single nuclear device could potentially shatter 2024 YR4 into fragments, or at minimum, vaporize enough surface material to create a thrust that pushes the remaining mass onto a different trajectory. But nuclear options come with enormous political, technical, and ethical complications. International treaties govern the use of nuclear weapons in space. Public perception of launching nuclear devices, even for peaceful planetary defense, would be contentious, and the technical challenges of designing, building, testing, and deploying such a system in just a few years would be staggering. Still, the research showed it was possible. If humanity decided it was necessary, we have the technology and the theoretical knowledge to attempt it. As of now, in December 2025, the situation remains uncertain. The 4% lunar impact probability hasn't changed significantly. More observations will be needed when 2024 YR4 comes back into favorable viewing position. But that won't happen for several months, possibly not until late 2026 or early 2027. So we wait, and we plan, and we hope that further observations will rule out lunar impact just as they ruled out Earth impact. But this experience has taught us invaluable lessons. First, the detection systems work. Atlas and other survey programs are finding these objects. The automated systems are flagging potential threats. The global network of amateur and professional astronomers is coordinating observations. Second, the threat assessment protocols function as designed. The Torino scale provided a clear communication framework. The International Asteroid Warning Network issued its first ever official alert, and the system operated smoothly. Third, we have the ability to mobilize world-class resources when needed. Directors' discretionary time on major telescopes was granted. The James Webb Space Telescope was tasked to observe an asteroid, something that had never been a priority before. International cooperation worked, but the experience also revealed weaknesses and gaps. The time from discovery to potential impact, just over 7 years, is barely enough to mount a deflection or disruption mission. If 2024 YR4 had been on a certain impact course with Earth, we would have been scrambling to respond. 3 years to develop a reconnaissance mission is cutting it very close. 2 to 3 years for a disruption mission leaves almost no margin for error. We need better, more sensitive detection systems that can find these objects earlier. We need spacecraft and mission concepts that can be activated quickly, perhaps even kept in a state of readiness. We need international agreements on decision-making processes. Who decides when to launch a deflection mission? Who pays for it? What if different nations disagree on the threat level or the appropriate response? And we need to expand our thinking beyond just Earth impact The 2024 YR4 scenario introduced the concept of lunar impact threats and orbital debris hazards. As humanity expands into space, as we establish lunar bases and Mars missions, as the volume of satellites in orbit continues to grow, these secondary threats become increasingly important. There's another aspect to this story that deserves attention: the scientific value of 2024 YR4. Even if lunar impact is ruled out, this asteroid represents an extraordinary opportunity. It's a pristine sample of early solar system material. Studying it up close could reveal insights into planetary formation, the delivery of water and organic materials to early Earth, and the nature of potentially hazardous asteroids. A reconnaissance mission to 2024 YR4 wouldn't just be about threat assessment. It would be valuable science in its own right. Some researchers have suggested that 2024 YR4 might not be what it appears to be. The unusual albedo variations, the rapid rotation, the way it was discovered, and the strange behavior of its impact probability curve. Could there be something we're missing? One hypothesis suggests the asteroid might have an irregular composition, perhaps with metallic inclusions or patches of different materials on its surface. This could explain why different telescopes saw different reflectivity values. It might indicate a complex formation history, possibly a fragment from a larger parent body that experienced differentiation, where heavier metals sank to the core while lighter materials rose to the surface. Another theory proposes that 2024 YR4 could be a contact binary, two objects that merged at low velocity and are now barely held together by gravity. This would be consistent with the fast rotation if the objects are tidally locked in a specific configuration. It might also explain some of the observational anomalies. But there's a third possibility that some scientists have quietly discussed, though few are willing to state it publicly. What if 2024 YR4 isn't entirely natural? Now, before you think we've entered conspiracy theory territory, understand that this isn't about aliens or UFOs. It's about the possibility that this object might have undergone some process, natural or otherwise, that altered its properties in unexpected ways. Space is full of surprises. We've discovered asteroids with rings, asteroids with moons, asteroids that are essentially flying piles of rubble, held together by forces we don't fully understand. We've found metallic asteroids that might be the exposed cores of destroyed protoplanets. We've observed interstellar visitors like Oumuamua that defied easy explanation. 2024 YR4's properties, while unusual, aren't impossible to explain with conventional asteroid science. But they're intriguing enough that some researchers have suggested the reconnaissance mission should include instruments capable of detecting anomalies, just in case. The public reaction to 2024 YR4 has been fascinating in its own right. When the Torino Scale Level 3 classification was announced in January, social media exploded, but the response wasn't uniform. In some quarters, there was genuine fear. People made emergency preparations. Some even considered relocating, though where they thought they'd go to escape a potential asteroid impact remained unclear. Survival supply companies reported increased sales. Online forums dedicated to disaster preparedness saw traffic spikes, but equally prevalent was skepticism. Many people simply didn't believe the threat was real. They pointed to past predictions of doom that never materialized. They questioned whether scientists really knew what they were talking about. Some suggested the whole thing was a manufactured crisis designed to increase funding for space programs. This highlights a critical challenge for planetary defense. How do you communicate an uncertain but real threat to a public that's simultaneously skeptical of scientific authority and prone to panic when that authority confirms something dangerous? The 3% impact probability was real. It was based on solid observational data and rigorous mathematical analysis. But 3% also means 97% chance of no impact. How do you motivate appropriate preparation without causing societal disruption? Space agencies walked a tightrope. They needed to be transparent about the threat while avoiding both panic and complacency. They largely succeeded, but it wasn't easy. Press conferences were carefully crafted. Statements were vetted by communication specialists. Scientists found themselves giving interviews to media outlets that had never covered asteroid science before. And then there were the cultural references. Almost every article, every news segment, every social media post mentioned Deep Impact, Armageddon, Don't Look Up, or some other disaster movie. The generation that had grown up watching those films was now living through a real scenario. Some found it surreal. Others found it oddly validating, as if Hollywood had somehow prepared them for this moment. A few pointed out the irony that the movies almost always depicted humanity coming together to face the threat, while real-world responses seemed more fractured and politicized. As the months passed and the Earth impact threat decreased, public interest waned. By the time NASA officially ruled out Earth impact in late April, most people had moved on to other concerns. The lunar impact possibility garnered far less attention, perhaps because it seemed more abstract, less immediately threatening. But within the space community, the conversation continued, and it expanded. 2024 YR4 had demonstrated that our planetary defense systems could work under pressure. But it had also revealed how much we still don't know. How many more asteroids are out there, lurking in orbits we haven't fully mapped? How many could be on trajectories that bring them dangerously close to Earth or the Moon? Current estimates suggest we've found about 95% of near-Earth asteroids larger than 1 kilometer. These are the civilization enders, the objects that could cause global catastrophe. Finding most of them is a genuine achievement. But for smaller objects, like 2024 YR4, the detection rate is much lower. We've probably found only about 40% of asteroids in the 100-meter size range. For 60-meter objects, the percentage is even smaller. And these objects, while not global threats, can still cause tremendous regional damage. There's a statistical certainty we need to confront. Earth will be hit by another significant asteroid. Not if, but when. It might be decades away. It might be centuries. But it will happen. The question is whether we'll have enough warning and whether we'll have the capability to do something about it. 2024 YR4 gave us 7 years of warning. That's barely adequate. Many mission planners say you really need 10 to 15 years for a properly prepared deflection or disruption mission. Less than that, and you're rushing, cutting corners, accepting higher risks. What if the next threat gives us only 2 years? Or 1 year? What if we discover it just months before impact? This is why some researchers are pushing for what they call a planetary defense architecture. Not just detection systems and mission concepts, but actual hardware, spacecraft built and ready to launch. Impactor vehicles in storage. Detailed plans that can be activated immediately. The cost would be substantial. Building and maintaining spacecraft that might never be used doesn't come cheap. But compared to the cost of a major asteroid impact, it's negligible. The Chelyabinsk event, from a relatively tiny asteroid, caused over $30 million in damage just from broken windows and minor structural damage. A Tunguska-scale impact on a city could cause trillions in damage and countless deaths. Insurance companies are starting to pay attention. Some are even beginning to factor asteroid risk into their long-term models. It's a small thing, but it's an indication that the threat is being taken seriously, beyond just the scientific community. So what did 2024 YR4 teach us? First, the good news. The systems work. Atlas detected the threat. The International Asteroid Warning Network coordinated the response. Major telescopes mobilized within days. The Torino Scale communicated risk effectively. International cooperation functioned under pressure. We passed the test. Barely. But here's what keeps scientists awake at night. 2024. YR4 gave us 7 years of warning. 7 years sounds like a lot, but to develop, build, test, and launch a mission to deflect or disrupt an asteroid, that's cutting it dangerously close. Most planetary missions take a decade. We had less than that. What if the next one gives us 2 years? 1 year? 6 months? And here's the really disturbing part. We only detected 2024 YR4 because we got lucky. It happened to cross our detection grid at the right time, at the right brightness, moving in a direction our telescopes were watching. Current estimates? We've found about 95% of the civilization-ending asteroids, the kilometer-sized monsters that could cause a mass extinction. That sounds great until you realize what it means. For objects like 2024 YR4, 60 meters across, we've probably only found 40%, maybe less. That means 6 out of every 10 asteroids capable of devastating a major city are still out there, undetected, untracked, moving through orbits we haven't mapped. Right now, at this very moment, there could be another 2024 YR4 heading our way. We just don't know about it yet. The universe doesn't care about our detection capabilities. It doesn't wait for us to be ready. Asteroids move on timescales set billions of years ago, following trajectories determined by the chaotic violence of the early solar system. And Earth sits in the middle of it all, a blue target in a cosmic shooting gallery. 2024 YR4 is still out there right now, moving away from us at over 50,000 kilometers per hour, growing fainter with each passing day. Soon it'll be too dim even for our most powerful telescopes. We'll lose track of it. The lunar impact probability will remain uncertain until it comes back into view. If it comes back into view. December 2032 is 7 years away. That's 7 years to improve our detection systems. 7 years to develop rapid response mission capabilities. 7 years to build the infrastructure of true planetary defense. Or 7 years to hope we get lucky again. Because, make no mistake, 2024 YR4 was a warning shot, a cosmic wake-up call. The universe just showed us that our planetary defense systems work, but only barely, and only when we have enough time. Next time, we might not be so fortunate. The generation that grew up watching Armageddon and Deep Impact now faces the reality those movies warned about. Except there's no Bruce Willis, no heroic last-minute mission, just scientists, engineers, and mathematicians racing against orbital mechanics and hoping they detect threats early enough to respond. Right now, somewhere in the solar system, there are rocks with our name on them, objects we haven't found yet, trajectories we haven't calculated, threats we can't see coming. The question isn't if another one will appear. It's when, and whether we'll be ready. If this story made you realize how fragile our situation really is, hit that subscribe button, because the next potentially hazardous asteroid could be discovered tomorrow, or next week. Or it might be heading toward us right now, invisible in the glare of the sun, and we won't see it until it's too late. Stay informed. Stay aware. The sky isn't falling, but it could be. Thank you for watching. And remember, 2024 YR4 is still out there, carrying its 4% chance of lunar impact, still potentially threatening everything we've built in orbit. The story isn't over. It's just waiting for December 2032. Keep looking up, because something might be looking back.